Okay, let's take a look at two example data sets before we combine data sets together. Let's take a look at the first data set X. So let's say that we have 1, 2, and 3, and the data is X1 is 5, X2 is 6, X3 is 7. Okay, so the sample size is 3, 1, 2, 3 pieces of data. Then the summarized information, what would it be? Sum X and sum X square, for example. So what will sum of X be? It will just be the sum of the three numbers, 5 plus 6 plus 7, 18. Sum of X square, each of the numbers you square before you put the plus between them. So sum of the squares. Then you get 110. Okay, good. Then variance of X, how to find? Well, variance of X we know is EX square minus square EX, right? But what is expectation? Expectation just means you take a sum then divide by n. So that's exactly what I do here. Sum divide by n of the X square. Expectation X in between the brackets first, so it's sum X over n in between these pair of brackets, and square outside. Okay, but this is really just this is the long-winded notation with the index I equal to 1 to n, I equals to 1 to n to refer to what? To refer to x1 square plus x2 square plus x3 square all the way to xn square. In this case, n is sample size 3, so it's just x1 square plus x2 square plus x3 square, which is really just this fella over here, sum x square, 110. So we can replace numerator with 110, divide by sample size n, which is 3, minus away sum of x, which we know is 18 here, right? Or divide by n, which is 3, bracket, then square. We can get an answer for variance of x. But take note that variance of x is really just sigma x bracket square. That's the other notation for it. Sigma square, right? The x there is just to tell you it's from dataset x. Okay. Can maybe we just compute the actual number so it's less confusing, fewer letters. Just look at numbers, maybe easier. So it's actually 2 over 3, Good. So okay, good. That's 2 over 3. Then maybe I should use blue color to be standardized. So 2 over 3. Then how do you calculate s square? So this is a formula from the MF26 over here. How to calculate the s square? It's really just 1 over n minus 1 times summation x square minus sum x bracket square, then divide by n. That's in the formula list. We're just gonna follow it. So n is 3, right? So that means that we end up with 1 over 3 minus 1, which is 2, times sum x square, which is 110. Sum x square is 110. Minus away sum x, what's that? 18. Bracket square divided by n is 3. Okay, type this in. This is your unbiased estimator of the population variance. So we get a 1. What a coincidence. Okay, nothing interesting, whatever. Move on. Now we look at data set y. Do the same thing, but this time it's 1, 2, 3, 4. Sample size is 4. I just changed the notation to little y to match up with this capital Y. Sum little y will just be a 9. Add the 4 numbers together. Sum y square will be, you square each of them, then you take a sum. It will become a 35. You can check it on your own later. Same thing, we calculate variance of y, which is, oops, wrong letter here. Shouldn't be x, should be capital Y. So ey square minus square of ey, which will be summation over n of the y squares and summation over n of the y's divided by, holding bracketed, then power 2. So this is just a more long-winded notation with the index I to refer to, in this case, n is sample size 4, right? So this will be summation of y1 square plus y2 square plus y3 square plus y4 square, all divided by 4. So we just use the summarized information. Sum y square is 35 on top, divided by n, which is sample size 4. Minus away sum y, which is 9, divided by n is 4, bracket power 2. Calculate. Let's see what this is. So to make our life easier later, we get the number first. So this is 59 over 16. Okay, nice. Move on. That is just variance. So we do the same thing to calculate the s square. So sample size now is what? Size is 4, right? Because it's data set y. So 4 minus 1, which is just 3 times summation y square is 35. Summation y square here. Minus away sum y, which is what? 9 bracket square over n is what? N is sample size 4. Type this in the calculator. Let's see what this is. 1/3 times 35 minus 9 square over 4. Okay, that's 59 over 12. Cool. Very good. Moving on. So now this is the two separate data. But what if we combine the data, right? What if we combine the data? So here's what we'll get. if you can go and scroll up and verify. 1, 2, 3 is, okay, I just relabel the index and I call the combined data set, call it T, T for total. Then I use little t here to represent each of the sample data, T index I. The first, the second, the third, and then I combine with the black color Y data, 4, 5, 6, 7, relabel the index. But the individual pieces of data never change. 5, 6, 7, then 1, 0, 3, 5. Oh, so this is really T1, T2 all the way to T7. Now sample size, well, now will no longer be 3 or 4. Instead, it's the sum, right? 3 plus 4 equals 7. Right? How about summation of T? It will be 5 plus 6 plus 7 plus 1 plus 0 plus 3 plus 5. See, I even color coded it. Blue color on the left, black on the right. This is sum x on the left, this is sum y on the right. Oh, so 18 plus 9 get 27. How about sum t square? It will be blue on the left, black on the right. This is sum x square on the left and sum y square on the right. Add together, you get 110 plus 35, you get 145. Okay? Then you can also calculate the, what do you call it, the sample mean or the unbiased estimator of the population mean, T bar, which is basically just adding everything together, happens to be sum x plus sum y, then divide by n from sample x plus n from sample y. The sample size of the data set x, which is 3, right? There are 3 pieces of data here. And then ny is the sample size of data set coming from y, which is 4, 5, 6, 7. So it's 4. 3 plus 4. Right, that's T bar. Then how do you calculate the variance? Do the same thing again lah, So sum t square over n minus way sum t over n bracket square. But this time we do something a bit more clever. Okay, this one not important index I. What's more important is to realize that sum t square here, from here, is really just sum x square plus sum y square, right? So it's this guy. How about my sum of ti? It's really just this part here, which is sum x plus a sum y. So sum x plus sum y, I substitute the numerator. Okay, good. Then from there, we know the general formula already. If you have separate pieces of summarized data, sum x square and then sum y square, you just add them together, divide by n. Then if you want, and then if you have sum x and sum y, you just add them together to get the total sum, which is really just using this formula but replacing this part here, sum of the ti squares, with sum x square plus sum y square. Replacing this other half of the formula, sum of ti, or summation of all the data, with sum of x plus sum of y. The data from data set x and the data from data set y, you add all together. And I forgot a square on the outside, sorry. Like this, Good. Okay, I got integral. Okay, not important. Ignore. But how do you calculate s square? Then in this case, s square is actually just not this formula, sorry. S square will really just be 1 over n minus 1, but this time n is what? The total sample size, which is 7 instead. So 7 minus 1. And then you multiply by summation of t square, which is, how much is it? 145 minus way summation x. T, summation t is 27, bracket square, divide by n. In this case is, what's my sample size? 7, right? Okay, then that will be your s square. So now that you know this general method, you have a sum x square plus sum y square instead of just a normal sum x square. And you have sum of, what is it? Sum of t, which is sum of x plus sum of y, instead of just a normal sum x. You can use this technique to tackle the actual question. So for the combined data, when you have 70 batteries, sum x 10317, 50 batteries, sum y is 7331, you just find the summation of the t, the total, which is sum x plus sum y. You get 1768. Then how about sum t square? You just do the same thing. Sum x square is this guy, sum y square is that guy, add them together. So 1540231 plus with the 1.1 million something. You get 2.6 million something. That's your sum t square. Then now we want to calculate the s square, but replace the x square in the formula mf26 with a t square. Okay, then instead of sum x, it becomes sum t for total. So all you need to do now is to sub in the formula. So n in this case is the total sample size. What is it? Let me see. 70 batteries plus 50 batteries. That's 120, right? So 120 minus 1. That's the denominator, 1 over. Then times the sum t square, which we already calculated above here. Minus away sum t, which is what? 17648. Bracket power 2, all divide by n. In this case, sample size is 120. The combined sample size. Then you can just type in the calculator with your to get your S square, right? Then for T bar, it will just be sum x of plus sum y divided by total sample size 70 plus 50. Maybe you can write down nx and ny, not so important notation. This one is more important. You get the summation of the total divided by number of numbers. Okay, then from there, you can continue with the test. I will not show. You will try it yourself. Have you calculate S square and T bar already? Now you have another question about the how to get the rejection region, right? Or aka the critical region. So how to do that? Here's what you need to know. Depending on the test, your H naught is always mu equals to something known as mu 0. On your GC, you'll see this mu 0. It's the exact population mean that is assumed by default in the null hypothesis. And then the alternative hypothesis mu. Then you have a inequality or something that's not equal sign followed by the mu naught. This guy can be three versions, right? It can be strictly less than, strictly more than, or not equals. Depending on which one you see, it's the particular type of test. Maybe I just swap this two around. This two is, okay, I label individually first. This guy is called a left tail test. That guy will be right tail test, more than. Then this guy is called a two tail test, not equals to. Together, left and right tail tests, they are called one tail test as opposed to a two tail test. Then the rejection region depends on what type of test you're dealing with. So remember the key rule to reject is p-value is less than alpha, right? That's method 1. Method 1. So how do you draw a picture to interpret this? What it means is that you must first start off with a bell curve. Because this is essentially doing z-test, so this is a standard normal distribution zn01. So that means that the line of symmetry must be x equals to mu equals to 0. Then alpha will be somewhere, we'll have some corresponding inverse norm value, right? Inverse norm value with area worth alpha amount. Okay, left tail area exactly equals to alpha. Then in order for p-value to be less than alpha, let's say we are doing a left tail test. Sorry, I should have started by saying it's a left tail test before I started shading the alpha. It's only a left, and because we're doing a left tail test, then that means that your alpha represents an area in the left tail of the graph that is equals to alpha. But for your p-value, a left tail area, to be less than alpha, that means that you will need to have a point over here. A z, let's call it CALC, z calculated, such that the area to the left here is exactly equals to your p-value, and it's less than alpha. So what does it, and so if you have this scenario, right, p-value, the blue one, is less than the green color one, the corresponding z coordinate, like x coordinate but change to z, z coordinate will be that, you will realize that you have your z coordinate z calculated to be less than the z, let's just call this z alpha, since it's related to alpha. But your p-value could be anywhere along here, right? It could be here, it could be here, it could be here, it could be here. In all these cases, the blue color left tail area will always be less than the green color area. In other words, p-value, blue one, less than the alpha, green one. So how do you describe this region here? All these possible values of z calculated such that p-value less than alpha, i.e. reject H0, i.e. the rejection region. This is also known as a rejection region or critical region. They come in many different names. Rejection region or critical region. The answer is set notation. Okay, so here's how you do it. You open up a curly brace, you close the curly brace. Make sure you have enough space. Then what you do is you label z an element of all real numbers. This is declaring to the world, okay, inside this set, curly brace means it's a set, I am going to see a lot of z's. But this z must obey certain rules. It belongs to the family of real numbers, no complex numbers involved. Okay, no complex numbers. Dot dot such that this z is very obedient. It follows certain rules. It doesn't just belong to real numbers. Very obedient, no complex numbers, very obedient. But it's even more obedient. It must satisfy certain rules. What's the rule? You must have z values which are less than your z alpha. What is z alpha? This guy you must calculate yourself according to the alpha given by the question. Inverse norm, area, mu, and 0, right? You can type in a calculator. You'll see it in the calculator. Area in this case must be your alpha. Mu and 0 must be 0, 1. 0 and 1. Because we're dealing with a standard normal distribution. Right? Your test statistic, x bar minus mu over square root of the variance, it follows, it's standardization already, so that means it follows a standard normal distribution. Mu is 0, sigma is 1. Okay? That's for left tail test. What if it's a right tail test? What if it's a right tail test? Just reverse the picture. Let me show you. I'm going to copy this. I'm going to paste this. I shrink it down. Then, now I'm going to do a mirror image. So how? It will look something like this. Instead of having a p-value green color area being left tail, it will be a right tail. So something like this. Okay, and then this value here will be our z alpha. Then you want p-value to still be less than alpha. This rule is still obeyed no matter which tail test it is. That's why method 1 is the preferred method if you have all the available information, because it's easier. But in terms of the z coordinate interpretation, for p-value to be less than alpha with a right tail test, it means that you need your z calculated to appear on the right side, and you have a right tail area, the blue one, as the p-value, exactly equal to the p-value. Green color area is alpha, blue color area is p-value. Okay? So if your, like for example, if your p-value is 0.02, it means that the blue color area is exactly equals to 0.02. You integrate from here until there, wherever there is positive infinity, you get the area under this curve, whatever the function, the curve is, the function, you will get a value of 0.02. That's what the p-value means. It's the area under this bell curve. Oh, I forgot to label the line of symmetry. X equals to mu, which is 0. This is a z n01 distribution. Okay, so how do you describe all these possible z values here such that the p value is less than alpha? It could be here, or it could be a bit more closer towards the alpha. Then you have a slightly bigger blue color p value area, right tail area all the way towards the right, but still smaller than alpha. Or it could be maybe, I don't know, somewhere slightly more towards the right, such that the blue color area is smaller, yet it is still smaller than this fixed alpha area, right? So there's all these possible regions that the z could be. So how do you describe this region? You just have to take this critical region. I'm going to duplicate it, but this time, all you gotta do is to change the direction. Boop. Like this. If it's a right tail test. Okay, then how about two tail tests? Not equal. Two tail tests, this one more challenging. So what you need to know is, now you still have the same interpretation that p value is less than alpha, which is exactly one of the steps in the method 1. Standard procedure, that's why you always use method 1 if you can. But if you really have to describe a critical region for a two-tail test, then here's how you interpret it. P value, right, will now be split up into two separate pieces. Over here, you have an area. Over there, you have area. The blue color area will now be P over 2, P over 2. They are supposed to be symmetrical. Does it look symmetrical? I hope so. Yeah. And then the alpha will also be split into 2. So here is alpha. There is alpha. Sorry. I say wrongly. There is alpha over 2. There is alpha over 2. Okay. You must divide it equally. So how do you describe this using neat notation? What you realize is that your z calculated can be here, or it can be there, right? Then this part here, this black line, is your z alpha, So how do you describe all this region towards the left and towards the right? Only one way. You don't know whether your z alpha, whether it's positive or negative, right? So if z alpha is actually negative, then the right side will be negative z alpha. If the z alpha was actually positive, then this left side will be negative z alpha, or the right side will be positive. So in order to make sure you guarantee you get the correct sign, you should put modulus first, then minus. Modulus first, then plus. Of course, you don't need plus anymore, huh? Right? Then how do you describe this situation? How do you describe this inequality? Here is the only way. You want z calculated. Sorry, I shouldn't be using the z calc because that's not a standard notation. I came up with that myself. I should be using set notation. You want all the obedient z's that are to the left side and to the right side, so that your p value will have p over 2 less than alpha over 2 on the left and p over 2 less than alpha over 2 on the right. There's only one way to describe this. It's this. Modulus of z is more than modulus z alpha. Does that make sense? So if you remember, mod x more than 1, how to open up? X less than negative 1 or x more than positive 1, correct? What if I change this 1 into a 5, and less than negative 5, more than positive 5, right? But what if I change this into a modulus 5? Don't worry, just bring along the modulus for the right. Just copy the modulus now. So negative modulus 5, more than the modulus 5. So now if I just replace the modulus 5 with what? Okay, step by step. Right, replace modulus 5 with z alpha, then that just means it's x less than negative of modulus z alpha, or x more than positive modulus z alpha. But what if I now replace the x, and x with a z, and z? That's exactly describing the situation we need. These two regions, right? Z less than negative of modulus z alpha, z more than positive of modulus z alpha. Right? So this is the critical region. And z alpha is to be calculated. Z alpha is to be calculated. You just inverse norm, whatever is the given alpha. The modulus z here is standard notation. This one to calculate. And this is your answer for the critical region. You just have to calculate what's z alpha and put a modulus there. Likewise for the left tail and right tail, you don't need the modulus. Okay, z less than z alpha, z more than z alpha, and then modulus z more than z alpha. I'll send you the notes. Left, right, and this is 2. Get the right tail a bit smaller. Maybe I'll just change it, make it look a bit bigger. Must have a graphic design. Cannot, this one. 0.02, not important. Must have graphic design. This one must appear on the left side. This one must appear on the right side. And this one in the middle, 2 tail. Okay, something like that. Okay, that's it.